After all this hard work in the previous chapters, that means implementing the data loader in chapter 2, implementing the attention mechanism in chapter 3, and then implementing the GPT architecture in chapter 4, we are now finally ready to train the LLM. We have waited so long for this, but yeah, finally we reached the section on training the LLM using the cross-entropy loss that we have introduced earlier in this chapter. So let's go through this step by step. I will introduce you to the main training pipeline first. So here is a figure that will conceptually explain what's going on before we dive into the code. So what we do is we iterate over the training set multiple times. So that is called a epoch. So one iteration over the training set is called one epoch. So that means if we're going through the verdict data set one time, that's one epoch. We could do it multiple times. That would be then multiple epochs. So it's a for loop. And then inside each epoch, we iterate over the batches. So this is essentially the iteration over the training loader that we've just seen in the previous section. What we do then, we first reset a computation called the loss gradient computation. And so this is something that might be a bit weird right now because we haven't done any implementations of that yet. So this is just something where we reset everything to 0. That's like a best practice in PyTorch, just, making sure we don't have any baggage from some previous runs, just resetting this. Then we compute the loss on the current batch. So this would be the cross entropy loss that we've talked about so far in this chapter. And then here, that's the core part where we compute the backward pass to calculate these loss gradients. So the loss gradients were briefly mentioned here. I will also show you where you can read more about loss gradients if that's a new topic in one moment. So, but just to finish this figure, we compute the loss. Based on the loss, we compute the loss gradients, and then using the loss gradients, we update the model weights, the weight parameters. So for example, in previous chapters, we looked at the nn.linear layers, and they have a weight matrix, nn.linear.weight, or our layer norm also has these parameters, and these are things that can be trained and optimized during the neural network training. And here model weights corresponds to all these parameters, like the layer norm parameters, the QKV matrices in the attention heads, the nn.linear layers, and so forth. And we use the loss gradients to update the weights to optimize the loss, which means minimizing the loss towards 0. And then optionally, we can train some statistics. So for example, the training and validation set losses and some other things to make sure the model is making progress. And then we can also visually generate text, have the model write some output text so that we can read the text and see if this is actually making sense or not, if the model finally learns how to generate human readable text. So this is the brief outline. And I mentioned loss gradients here. And if this is something that is not familiar to you yet, I don't want to go into too much detail in terms of explaining how all this works, because it's like a deep learning topic that would be a good topic for a different type of book. However, I mentioned this before, I have written an introduction to PyTorch here. Actually, this was originally the first chapter. It was like a 40-50 page chapter. But then I thought, well, this book is supposed to be about LLMs and not deep learning, because otherwise, it could be an infinitely long book. So I moved this chapter from chapter 1 to the appendix. But it's actually, I hope, a really nice chapter explaining how deep learning works and PyTorch works in a reasonable time frame, like 40-50 pages. And here, if this is all new to you, like computation graphs, loss gradients, there's actually a nice section here you may want to read through. And so here I'm explaining this with a simpler example with a trainable weight parameter and so forth. And then the target label, for example, in our case, the target token IDs, the computation of the loss, and then how we backpropagate this. So this is a calculus concept. I'm trying to keep it simple here for a simple neural network, because PyTorch takes care of this for us. So PyTorch is doing all this when we call .backward. So there's a method we will see in a few moments. It's called backward, and it will do all of this. And then we will update the model weights using the gradient. But You don't have to necessarily understand this. So if you are new to calculus and everything, I think it's nice to understand this, but it's not 100% essential. What is, I think is essential is that we are trying to optimize or update the weights such that the loss gets minimized, which then leads to the model creating more correct tokens, or ideally the target token IDs. So yeah, to show you how this works in code, let me just post the whole thing here, and then we will go through this step by step. So this function here, it's called train model simple. Why am I calling this simple? This is, yeah, I would say a relatively simple training loop, a minimalistic training loop. It does everything we need. And this is also what you can use, for example, to train a convolutional network for image classification or other types of neural networks. But it's relatively minimalistic because there are some other bells and whistles that you can optionally add to this if you want to. And so I've written about this here in Appendix D, where I'm talking about something called like a learning rate scheduler and gradient clipping and so forth. So this is more like, I would say, an advanced concept. So once, I think, if you finish chapter 5, you can optionally look into this. But, you know, it's not 100% essential to understand how pre-training works. So here, this is really like the big picture, the model training. And so what we have here, going through this step by step, is we keep track of certain things. For example, the training losses, validation losses, so we can look at them. Here we also keep track of how many tokens we have processed and how many steps we did, like training steps. And then here, this is the iteration over the epochs. If I go back to the figure I showed you earlier, one moment, here we go. There. So the first here, this first box would correspond to this first for loop. We set the model into training loop because before, when we played around with the model, we had it briefly in this evaluation mode. So it's actually a good practice at the beginning of a training loop to just make sure it's in training mode, which will then enable the correct behavior of dropout and so forth. Here we are now iterating over the training loader, similar to what we have done when we computed the training and validation set losses. Here we are resetting the loss gradients. So we are doing that because later we compute the loss gradients, for example here, and then for the next round, we are resetting it. I could also just, I mean, it depends really, it would do the same thing. If we have never computed them before, it would make no difference if we reset them after or before. So it's just, I think though, a good practice to have it just here in case you played around with the model and you accidentally computed something. So this is just like, a good practice to have it here. We compute the loss, the training set loss. So on the current batch, so we are iterating over the batch, and then we use our calc-loss batch function, which we already implemented in the previous section here. So it's a reusable function. By the way, in the book, in general, I made sure to minimize clutter so that we can reuse functions as much as possible throughout the book. So I think that helps also keeping track of what is happening. And so there are not too many concepts, keeping it as small as possible. But of course, sometimes there's a lot of code because it's necessary, but I'm trying to keep it also a bit minimalistic for, yeah, readability. And so here we compute the loss, that's the cross entropy loss. And then we do the backward. And so the backward, so I mentioned before, when we do call the model to create the logits, and the logits are actually created in this function. So where we are here. So here we have the logits that are getting created here in the calc-loss batch function. And I mentioned something like a computation graph before. So when I talked about the no-grad function, where we don't want to have this computation graph. So the reason why I didn't use the no-grad function inside this calc-loss batch is because now we actually do need the computation graph. For evaluating here, yeah, we don't need it. But here, down here, we do need this computation graph. So this is computing or creating this computation graph. And maybe one more time here. If I go, where was it? here. So this computation graph, if we have a computation here, in this case, a very simple computation like this, you can think of it as a simple model. It will create a computation graph like this one here. And in a similar sense, PyTorch will create this computation graph of the model when the data passes through the model. So let me just go through the model here forward. So here, when we call something like model X or model inputs, this will execute always the forward method. That's just how PyTorch is implemented. So based on what's done in this module, the behavior of a PyTorch module is always, when we pass input, that it goes through the forward method. You can explicitly also write it like this, but it's best practice to do it like this because there's some extra computation happening. But what happens is this gets executed, and this will result in a computation graph for these computations similar to what you're seeing here. And then PyTorch, when you do backward, it can calculate these gradients here. So this is the computation graph that's created during the forward call. And then you see there's this backward call, which will create this computation graph. Oh, sorry, the gradients from the computation graph. So that's computing the gradients. And then optimizer step. This will use an optimizer, for example, stochastic gradient descent or ADAM, to apply these gradients. So the gradients get multiplied by a learning rate, which is a hyperparameter that says how much we want to update. And then the model weights get updated, basically. So if this is all new to you, it's maybe not a bad idea to go through this introduction to PyTorch and the brief introduction to deep learning. I do have also this whole class on deep learning that might be interesting to you. I have actually multiple classes. So this is very slow right now, but I have multiple classes also. So there we go. If you're interested, this one here or this one here, they both go through the concept of deep learning and explaining this a bit more detailed. But if you are short on time and you want to just get the basics, I think Appendix A is actually a good way to start. So you can read this maybe in a few hours instead of a few weeks or days. So that's like a nice short introduction. So, but yeah, back to our training function here. Then we just increment the tokens we have seen, the global step, how many steps we have taken. And why we need the step here is I'm just using it for optional evaluation. So I'm saying if we have evaluation frequency here that we can set here, for example, every 10th step, if we set it to 10th, every 10th step, it will trigger this code. And in this code, we evaluate the model. So we evaluate the training and validation loss here. We append the training and validation losses to our list just for record keeping, so we can plot that later, and the number of tokens. And then we also just print it out so we can see the progress. And then this is happening for each batch here. And this is happening every 10 batches, essentially. And then every epoch, so here for the outer loop, for every epoch, we are also additionally printing a small sample, like just giving it some sample text and see how the model is doing. So the evaluate function here for completeness, it is similar to what we have used before. So it's similar to this calc loss loader here, except we are using it twice. So we are calling it here once and twice, so to get the training and validation loss, and so we can compare them and see if the model is overfitting. And then this generate and print simple function, it puts the model into the evaluation mode. By the way, here it's also so to disable dropout and everything. Then we essentially encode some sample text, similar to what we have done at the beginning of this chapter. And then again, similar to the beginning of this chapter, we call the generate text simple function. And then we decode it and put it back into training mode. This might not be strictly necessary because we already have train here, but it never hurts. It would just skip it, but it's not a bad idea sometimes to do it, so in case we forget or something. So yeah. And so this is essentially the training function. And then let's call this training function. So we are initializing a new model. Here we are using the random seed so that you get the same results that I do. So for the initial model weights, here optionally we put the model onto the device. So here personally I'm just running this on a CPU, but you are welcome to run this on, if your computer supports it, on a GPU or the MPS device that I mentioned, if you have a MacBook or Mac Mini or Mac Studio or something like that. However, you might get slightly different results. It will be faster. The results might not be 100% the same, but it's something you can still do. I'm just doing the CPU version here because, just to show you what numbers you would get on a CPU and GPU. Because GPU, based on my experiments, you get the same results as on the CPU. Here we have a Adam optimizer, Adam W. So that is an optimizer, a version of Adam with weight decay. Again, it's like a deep learning concept. I do think I covered it in my lectures. If you are curious, there should be something on Adam somewhere. So, but it's not strictly necessary. You can think of it as a way of computing the gradients and applying the weight updates essentially on the model parameters. And the learning rate is how fast the model learns. So this is instantiating the model and the optimizer, which we pass here, here and here to this train simple function. And we are going to train for 10 epochs. Why 10 epochs? It's just something that happened to work well. So in reality, when you train a real neural network, for example, I don't know, Gemma 3, Llama 3, and so forth, they train these networks on 14, 15 trillion tokens, or DeepSeek version 3, which will cost you a few $1 million and will cost or will take thousands of GPUs and take months of your time. So I assume you don't have millions of dollars and months of time and thousands of GPUs. So we are keeping this example small, train this only on a single book, The Verdict, the short story. And because this short story is so short, one epoch would not be enough to get the model to learn anything useful. So I'm just increasing it to 10 epochs. But, like normally people train models for 1.5 epochs max. Usually it's just one epoch because the data set is like 14 trillion tokens and so forth, trains for months. And so here we just keep it small to make it cheaper, but then we need a few more epochs to see that the model is actually learning. And then, we will have a start context, the familiar every effort moves you, and see if the model can create more comprehensive text compared to what we had before. So I think before it was just generating gibberish, and now we will hopefully see that the model generates better results. I hope this actually runs because I'm actually recording this video also on this MacBook Air, and this is at its max already with the camera and this screen capturing. So I hope this will work. We will see. Of course, the familiar problem. Okay, so let's see. It might take a few minutes. So I remember when I was running it without any recording here on and everything, it took about 4 or 5 minutes, so it's pretty fast. But we'll just wait and see. So we can see now that the model is not generating anything useful, but what we can see at the same time, what is actually good and what we want to see is that the loss is going down. So we can see the training loss and the validation loss, they start off high and they go downwards, which is good. So we want to minimize the loss so that it reaches or it goes towards 0. You can see it's still not doing anything useful. It's generating words, but it's repeating the words, not anything useful yet. And by the way, I don't know if I talked about this before, but the model we are training in general, the pre-training, trains the model to just keep on generating text. So it's also called like a text completion model. And this is true for basically all LLMs. Later on in chapter 7, we will train the LLM to follow instructions. So that's a separate step. It requires a separate approach. So right now we are only pre-training to generate the next word in some text. So if we provided some text, it will just keep on talking like me at the moment. But later in chapter 7, we will also learn for the model to how it follows instructions, and it will also then have a stop token to stop generating text. So we can see, yeah, it is already, I would say, getting slightly better. So it's not, at least not repeating the words anymore. So it is generating something. He had the donkey. I mean, it's improving at least. So we see it's getting better if we consider that it first just generated commas and then ands and so forth. Yeah. And we can also see the training loss keeps going down, but the validation loss gets stuck around 6. This is kind of expected because we have a very small data set. And so the model sees the training set multiple times, it starts overfitting. So if we had more data, like I do actually have an example. Let me, in the meantime, while this is training, go here and show you some bonus material. So I do have an example here. I have a lot of bonus material, as you can see. So there's the alternative weight loading, which we will get back to later. I have a pre-training of the model on the whole Project Gutenberg dataset. So Project Gutenberg is a website of public domain books. There are lots of datasets out there, but you know, the copyright debate is still going on, whether it's allowed to train a model on certain data. So here, this is only public domain data, which should be fair to use in the US. So here I have like an example. I think I trained it for 1 or 2 weeks once, and there you don't have that overfitting, of course, because the model sees different texts each time, so the training set doesn't repeat. What I also wanted to mention is, yeah, hyperparameter optimization, if you're interested. This is maybe also nice. We'll not go through this, but this is just adding an interface to the LLM. So you can then type it similar to ChatGPT, and the model responds in a visual interface. So it's just a little add-on here to our model once it's finished training. But yeah, I'm not going through these all because this is optional material. You can exploit maybe afterwards. What is interesting is maybe I actually, just for fun, we coded the GPT architecture in chapter 4, but I also coded the Llama architecture, went through this step by step. And so if you're interested in training a Llama model, Llama 3 model, you can use the same training function. So everything is the same, just a different model. What I wanted to talk about, here. So I also have some bonus material on making the training faster. So I mentioned before, I kept everything very simple, very vanilla. So it runs on any computer. It also runs on a single GPU, but it's not optimized for efficiency. It's just optimized for learning. And here I have some bonus material where I make some changes to the code, and it will make it significantly faster. So you can read through this. There are, I think, 10 tips to make the model much faster. So if you're interested in that, so before I was measuring the speed in terms of tokens per second. Before it was generating 142, was going through 142,000 tokens per second. And then here it's about 4 times faster afterwards. So it's a very big improvement. Well, actually, this is for multi-GPU. Okay, sorry. So of course, multiple GPUs make this 4 times faster, approximately 3 point something times faster. Here's the speed advantage, so 142,000 tokens after the 10 steps. And before it was just doing 12 tokens. So it's like 10 times slower. So I made it basically 10 times faster by applying these tricks. But something like this, it might not work on any, not on every computer, because it has some requirements. For example, also bfloat 16. This should actually work now, I think, on most CPUs. But you can work through this on your own time. This was optimized for GPUs, and bfloat 16 doesn't work on every GPU. I think the GPU has to be an Ampere, like A100 or H100 or newer. I think L4 or L40 also works, but older GPUs, like what do they call it? Like the T, I even forgot the names. The T model GPUs, they won't work anymore here with this bfloat 16. But anyways, it's a topic for a different time. I was just trying to pass the time where our model was training here, but I can see it's now finished. So what we can see is the training loss went down, and we have actually a very small training loss, which is nice. Validation loss is high, but can't have everything with a small example data set. So it's a trade-off we make for having something that trains in just 5 minutes instead of 5 months. And yeah, you can see the text kind of makes sense. So what it says is every effort moves you. No, was one of the axioms he laid down across the so and so and so. You might get slightly different results because I may also have changed certain things compared to the book while I was typing this here with the random seed and the data set and so forth, the shuffling. But I think it should, in your case, at least get something that is in the right ballpark here. And then just to wrap up this section, because I know it was a very long section, I was talking a lot here. I wanted to just also add a plotting function. So this is just a matplotlib plotting function that will plot the number of epochs, the training losses, and then just visualize what we are looking at here in this text. So let's see how that looks like. And by the way, this is why I was keeping track of everything here and here, especially the lists, because I'm returning them here at the bottom here. Training losses, validation losses, track token scenes. So I'm returning them from the list here. So we save them here so that I can visualize them here in matplotlib. And yeah, we can see the training goes down towards 0 like we want. Validation, it's struggling a bit, it's going down, and then it's getting stuck. So that means that the model is overfitting. But again, it's because we have a very small data set for educational purposes here, just so that it doesn't take too long. But this is something you can also apply to a larger data set, of course. Okay, I think this is it for this section. In the next section, we will talk a bit more about the sampling, because so far we only used a very simple sampling procedure, and I will explain some alternative ways we can implement to generate text.
Get this book at Manning.com.